talk through this homework on a little bit on Darcy's Law and then on equilibrium wells. So the first problem is a Darcy's Law problem. You have a column with the dimensions given, and first it asks for the pore volume. Well, you can come up with the whole volume by taking the diameter and the length of it being 30 centimeters. So you can come up with the whole volume of the column, and then the pore volume is the volume of voids, or the total volume times the porosity, 0.31. So we call that a pore volume. Hydraulic conductivity, again, this is a Darcy's Law problem, so Q equals K A change in head with length, and we'll probably put a minus there because the gradient is negative. So we have the flow, 3 cubic centimeters per minute, 3 milliliters per minute. We have the head loss, 45 centimeters in a 30 centimeter column. So you have the hydraulic gradient. We have the area is the cross-sectional area, so pi over 4 times diameter squared. So the only unknown there is the hydraulic conductivity. I guess it's be minus 45 over the specific discharge, or the Darcy velocity. It's little q equals q over a. So you just take the flow divided by the cross-sectional area, and that's a step on the way to the flow velocity, the transport velocity, v sub s for the seepage velocity, sometimes vx in the x direction. That's the actual velocity. So remember that v sub s is the specific discharge divided by the porosity, because a velocity, remember, is a flow divided by the area, and the area of flow would be the porosity times the whole area. So this is the whole area for the specific discharge, and then for the seepage velocity, it's the part of the area that's open, which is the porosity. The time for one pore volume. Well, so you can do that a couple different ways. So you have the pore volume, right? So that's going to be, I forget what the number is. It's 50 milliliters or something like that. And then you're pumping through it at the flow rate. If it's 50 milliliters and you're pumping 50 milliliters per minute, well, then it takes 1 minute. Or you have the length of it, and you know how fast it's going, right? If you're going 60 miles an hour for 30 miles, it's going to take you half an hour. So either way, you'll get there. Now, let's change the numbers a little bit. Now that with the K that we calculated above, now go to, if we change Q, so Q becomes, what was it before? It was 3 cubic centimeters per minute, 3 milliliters per minute. We up that by a factor of 10. Well, if you look at the Darcy equation, if this goes up by a factor of 10, the K is for the material, the A is the same, hydraulic gradient is going to have to go up by a factor of 10. DL, I guess we'll call it. And same kind of thing with the same K, we change the hydraulic gradient. So before it was 45 centimeters per 30 centimeters, so 1.5 centimeter per centimeter. If it goes up to by a factor of 4 to 6 centimeters per centimeter, then your flow rate would go up by a factor of 4. The rest of these are equilibrium well equation problems. So this first one, we have a pumping well, and we have 2 different observation wells at different radii. So you can calculate that. We have the depth to bedrock, 60 feet, ground surface. Initially, the water level is 4 feet below the top of the well. All right, so we have our well here, and we said that it's depth to bedrock 60 feet, so it's 60 feet up here, and then we have initially its water level is 4 feet below. This is 60, this is 4, I guess that would be 56 feet, right? It would be H0. And then we start pumping it for several weeks, so we get to the equilibrium condition. Like I keep saying a little bit, we're going to go to the transient condition. And then we measure the water levels. The water level is 12 feet deep. What does that mean? That means 12 feet below the ground surface, or below the top of the well, rather. So it's 60 feet up, 12 feet down. So that would give an H1 of 40 feet and an H2 of 50 feet. And then you can get the radius from the grid squares there and find that. So just use the equilibrium well equation. Yeah, I'm looking over to my notes here. I have it written down. You should have this in your notes. You can solve that for hydraulic conductivity, Q over pi, and it's a log of R2 over R1 over the H2 squared minus H1 squared. That should give you the hydraulic conductivity. Now, rearranging that equation, we have it. You should have it also in your notes, rearranged for the head. First of all, you have the radius, you have the heads, you have the flow. You can calculate the hydraulic conductivity. Plot that. So it should look like, if you plot it, so plot drawdown versus radial distance. Plot is negative. So if it's drawn down 20 feet, it would be minus 20 feet. So make it look like that. So that's what the actual drawdown looks like. What is the approximate radius of influence? Solve this. Now that you have K, you can use one of your other H's for R with H equals H0, which I guess is 56 feet, number away. What is the drawdown at the well? So solve for H, and then you get the drawdown is H0 minus H at the radius equals, and what size is our hole here? 8-inch diameter well. That's actually the diameter of the hole. So 8-inch diameter well, the radius of the well would be 4 inches equals 1/3 of a foot. Now we'll change the Q. Well is pumped so that it remains empty and it looks like the radius of influence is 500 feet. So part F, what do we have? R2, one of our R's is the radius of influence, and the head equals H0 equals 56 feet at that point. And then at RW, again, that's 0.33 feet. H equals 0. Can I have an H of 0? Yeah. So I can have one of these numbers and then one of these be 0, and one is 56. We square it. I can't have an R of 0, but I can have an H of 0. So plugging all that in, keeping the same K, plugging those R's and those H's in, solve for Q. Just fun with the equilibrium well equation, putting it upside down and backwards and forwards. Next problem, we have a confined aquifer. We have an aquifer thickness of 60 feet. The well is pumped at, given the rate there, drawdown was observed at 7 feet. So we have R2 is 5,280 divided by 2, half a mile. We have a drawdown of 7 feet. Drawdown is initial head minus head after pumping. So we have that at 2 points. We have it at half a mile, and then we have it at 100 yards. We have a drawdown of 25 feet. So the confined equation, you'll have this in your notes somewhere, we can solve for the transmissivity. It's Q over 2 pi. So we get a 2 pi in this case. We just have 1 pi in the unconfined case. And then our heads are not squared, so we can actually have H2 minus H1 is the same as S1 minus S2. So flip the order of there. This is always positive, so if you come up with a negative, you just do the reverse of those numbers there, times the log of R2 over R1. So you should solve for T, and then T equals K times the aquifer thickness. So then K would be the T over B. And ask for a couple different units there. So do some unit conversion to get there. So the last one is a plug and chug one on the unconfined case. So I say the groundwater table elevation. So I don't tell you it's unconfined, but you should be able, from that description, groundwater table, you should be able to tell that it's unconfined. It was a plug and chug on the equation, and I think you have Q over pi times H2 squared minus H1 squared times the log of R2 over R1. You might have to convert some units there. All right, if you have any questions on this homework, let me know.